Okay, so last time we talked about certified poisoning defense. Specifically, we're talking about fixed defenses where the visible set does not depend on the poison. There are some examples. For instance, you can design the visible set to be licensed words, contain only licensed words, or other kind of scenarios that's designed that's basically trying to design a rule that is not dependent on data, basically. So now we have this data dependent defenses. So it's that you're designing the feasible set based on the poisoned data, right? So that's the union of the poisoned and the clean data. So the goal is really to estimate the P star from the poisoned data. And the caveat here, now this becomes really a game between the defender and the attacker, because the attacker, knowing that, so the defender is actually using the poison data to design the feasible set, then could try to manipulate that, right? So let's see. We already talked about this last time, that you are trying to maximize this loss function of theta hat, which is estimated using the data that you observe. So you finally get an M that you wanted to upper bound so that you get a so-called certified defense. That's the key for the certified defense. So we said in the fixed defense scenario, this really boils down to a single point that maximizes the loss in the feasible set. So as you can see here, right, this is just a review of last lecture. You will see that this epsilon maximum of this L theta the XY, where the XY is within the feasible set. So everything boils down to finding a single point within the feasible set. And now if you have epsilon n such points, then all of them are going to be the same, because you're simply trying to minimize the loss in your training. Okay, so again, we talked about the algorithm 1, which is the online learning algorithm for generating an upper bound and candidate attack. So you can see that there's this computing x, t, y, t, right? So, but overall, this is simply just trying to find feasible set that is maximizing your current loss function based on your current theta, t minus 1. But why this is an online algorithm? Only because your choice of xt and yt should also depend your current model, theta t minus 1, right? So if it doesn't depend on the, if the current model changes, then of course your poison data should change, because the model changes, then the loss function would change. Then how do you maximize? Which data point was in the feasible set that would maximize the loss function would definitely change. So that's only the reason why we have like an online learning algorithm for generating upper bound and candidate attack. Simply because your learning algorithm is evolving, basically. Not your learning algorithm, sorry. So your learning is going on, so your learned parameter is evolving. Okay. So we have this proposition 1. I don't want to spend time now here, but now let's move on to data dependent defense. So the data dependent defense, basically, the difference is, again, like I said, is the feasible set depends on the poison data. So DP union DC. Well, in this paper, so what's really interesting about this paper, it doesn't necessarily give an algorithm, but it gives a framework to understand certified defense in poisoning. Okay, so this is more like a general framework that can be used to evaluate certain kind of defense mechanism. So this one using an example of a slab defense. So we can see what is a slab defense. Basically, is project points onto the line between the centroids, then discard points that are too far on the line. So mathematically is this equation 7, but I've drawn a figure down there. So you can see in figure 7, sorry, in equation 7, you have this u hat y sub y of dp, and you have sub minus y dp. Okay, so what are these two? So this u hat y dp is just the empirical mean over the Poisson data, right? So the clean and the Poisson. So basically it's this guy, right? So this is the centroid empirical mean. And these are the points. I don't know whether they're clean or Poisson because I just don't know as a learner. So what I can do is I can just estimate all the data that are, labeled as positive, but estimate the empirical mean. So this is what I'm getting, all right? I'm getting this purple dot here. Similarly, I can do that for all the negative examples. So I get this blue dot here, right? This is my empirical mean. So what I'm doing is essentially whenever there is a new data, when for every data point, x, y, I can just do a projection, right? I can just project it and see whether, so there is a parameter sy here. So the sy is just saying whether my, it is a criterion, it is a hyperparameter in my slab defense algorithm that helped me to decide whether the projected, whether the points after projection is within my feasible set or not. Okay, so this is hopefully clear.
Can you go over what mu negative y is again?
Can you say that again?
Could you please go over what mu negative y is? I know that mu y is the empirical mean.
So you look at the figure here, these are the positive examples, these are the negative examples. Centroid of positive examples is u hat sub y, and centroid of the negative examples are u hat minus y. Is that clear? Is that clear? Is that clear?
Yes.
Okay. I don't know who asked this question, but I hope that's clear to her. Okay. All right. So now this is the slab defense. Similar to the fixed defense. So you wanted to find an upper bound of the M, right? Whether this is data dependent or not. Anyway, you wanted to find an upper bound of the M. So you can still use this theorem we talked about earlier, right? This max mean inequality, right? So once you use the max mean inequality here, right? So then again, you will get this upper bound on this M here. Now, however, this case that optimal DP places all points at a single location is no longer true for this adaptive case, right? For this data dependent case. So we must jointly maximizing over the full set DP, right? So you can see the difference here. Here you are placing everything, you are basically saying you wanted to find the worst point within the feasible set. This is for fixed defense, right? Because your defense doesn't depend on DP, but now it depends on the DP. So that's a different story, and that's the major difference between the two. Okay, so now if you see that, you will see, so equation 8, so you're trying to get an upper bound of this M, and you denoted that as minimal of theta u tilde of theta. So what is u tilde of theta? Is just defined as, the clean loss, the empirical clean loss, plus what is this epsilon? Why do we have this epsilon? right? Because we have epsilon n such data points, right? So, and divided by n, it is just epsilon. So this is just like a weight. You have if the epsilon maximize this thing. So what is it? The maximization is such that you want to maximize this expectation over the loss. And the expectation is the pi, the pi p. What is the pi p? The support of the pi p is just going to be a subset of the feasible set. Okay, so we take a continuous relaxation. Think of dp as a probability distribution with mass 1 over epsilon n on each data point in dp, and then relax this to allow any probability distribution. So that's what we're doing here. So essentially, in order to get a certified defense, you're simply trying to minimize this. Well, there is a maximization here as well. Okay, of course, there are a few caveats here. So overall, that's what I wanted to talk about this paper. But so one thing I wanted to emphasize is that this paper doesn't propose a specific algorithm for defense, for certified defense. Well, it uses the data slab, the slab defense, right? So as an example, to show how to certify the performance of a defense for poisoning attack. But it doesn't really specifically try, the contribution is really not really to introduce an algorithm. So now the reason why I talk about this algorithm is because first, a lot of us are interested or have already worked on or heard of at least certified defense in evasion attacks, right? During test time, you can have perturbed examples as the test examples. So during test time, you wanted to do certified defense. Well, certified defense basically means that, based on some kind of mechanism that you can do to improve your classifier, or by, transferring the classifier to a smoothed version, or by trying to manipulate a upper bound of the worst scenario so that, you can minimize that upper bound during training. So by doing all these kind of defense mechanisms, I hope that during test time, the perturbation allowed so that the prediction is still accurate is larger. So I'm allowing larger perturbation so that within the perturbation, no matter what kind of, within the radius of the perturbation, no matter what kind of perturbation you implement, the algorithm would still be accurately making a prediction. Okay, so that's the so-called kind of defense mechanism. But in poisoning, this is a little bit different, right? And that's why I wanted to talk about this. I didn't have time, unfortunately, to talk about evasion attacks, defense mechanism. But hopefully, by talking over this paper, we have a good understanding of during training how we can certifiably defend against poisoning when the training data could be poisoned. Okay, so basically this concludes our discussion on the line, basically the first part of this course. I would characterize the first part of the course as we started with learning theory, statistical learning theory. We learn about concentration bounds. We learn about the generalization gaps. We learn about complexity of hypothesis sets. Once we're equipped with this basic tools in classical machine learning, we started to use these tools to understand deep learning models. We understand, the generalization ability of deep learning models. We also understand the robustness, of the deep learning models when there were adversarial perturbations. So that characterizes the first part of the course. Now I'm going to go to the second part of this course, which is starting with graphical models. But this graphical model is, again, just an introductory material. Our real purpose, the ultimate purpose of this course for the second part of this course is to introduce the latent variable models and introducing a suite of spectral methods that are guaranteed to be consistent for a very wide set of latent variable models. So the reason why I wanted to do that is there are some nice connections between latent variable models and deep learning models. Actually, I was hoping that, by finishing talking about the second part of the course, we might be thinking about the following open question, which is, given all this very well understood methods in latent variable models, can we somehow use them in learning deep learning models? Can we use these methods in deep learning methods? Actually, many of my a few projects in my group, research projects in my group, my students are working on, are already talking about some of these issues, right? For example, using tensor representations in deep learning, right? So, to improve generalization. We're also talking about spectral methods, for maybe understanding learning of deep learning models, rather than just generalization. Also, maybe, you kind of wanted to use spectral methods to explain why certain kind of deep learning models work, or whether the existing backpropagation optimization is necessarily the best approach we can use to make them converge better, right? So there are a lot of open questions, but nonetheless, I'm going to start with the introduction of graphical model, and then we will go into the latent variable models. So today, I hope from now on we'll start with the graphical model. Okay, all right. Any questions before I proceed? Okay, so graphical models are really, when you think about graphical models, think about two major classes, the directed graphic models and undirected graphic models. So directed graphic models often, also you can call it as Bayesian networks, and sorry, not Bayesian, Bayes networks, and then belief networks, causal networks, and so on, right? Whereas the undirected graphical model, oftentimes you could call Markov random field, or conditional random field, and so on. Sometimes you also call it Markov networks. So these are just like some other names for directed and undirected graphical models. And here I'm showing just two examples, one for directed graphical model, and the other is for undirected graphical model, right? So, the nodes and edges basically characterize it. But why do we care about graphical model, right? So for those of you who haven't learned about graphical models, why do we even think about them? How does that relate to machine learning? So before we go there, we first need to understand some advantages and disadvantages of directed graphical model versus undirected graphical model. So the advantage of undirected graphical model over directed graphical model is usually, because the undirected graphical model is usually symmetric. So, if I am connected to you, then you're also connected to me. But in directed graphical model, the connection is one directional, right? So undirected graphical model is symmetric, therefore natural for some kind of spatial relational data. Although I haven't told you how we can use graphical models for them, but this is just the basic idea that you can use them for some spatial and relational data. And this discriminative undirected graphical model, people oftentimes call it conditional random field, sometimes work better than discriminative directed graphical model. Of course, I don't have the details here, but I just wanted to give you a general idea. So disadvantage of the undirected graphical model over directed graphical model is as follows. The parameters are less interpretable and less modular. And the parameter estimation is computationally more expensive, right? Because of the symmetry, actually. So now let me first introduce some basics in Bayes networks. So also using Bayes networks, I wanted to motivate why we use graphical models. Okay, although this motivation also works for undirected graphical model. So Bayes networks, so think about this question: how do we compactly represent joint distribution over a set of random variables, right? So oh, there is a typo here, so I shouldn't have the P here. So, over the set of random variable x, x1, x2, and xd. Actually, I think I should say xp, but anyway. So, how do we represent compactly represent joint distribution? First of all, why do we care about the joint probability, right? So consider this Bayes optimal classifier. So this is probably one of the most important classifier as you were introduced to machine learning. Maybe in your undergraduate machine learning course, or if you've learned machine learning on an online course, this would probably be one of the few most important classifiers you've learned. So consider this Bayes optimal classifier. What is it? Just to recall. So you have this y hat. You want to estimate the y hat, which is the argmax of this conditional probability, right? Conditioned on your x, it's some observation x, and your y, you wanted to maximize the probability of y under this observation of x, right? This is what your Bayes optimal classifier is doing. Now, if you just write it using the chain rule, you can see that very easily it just can be rewritten as y being the argmax of the conditional probability of x given y, and multiplied with the marginal distribution of the y divided the marginal distribution of the x. Okay, so this is very simple chain rule. So I think I wanted to clarify one thing here. So let me. So let's say I have, random variables x1 from x1 through xp. So I have p such random variables, and each one of them could take values from these integers from 1 to d. Okay. So sorry about this typo here. So now my question is, if xi can be taken values from these discrete integers from 1 to d, then what's the number of parameters you need in order to characterize this probability, this conditional probability? So the probability of x given y equals to y. First of all, if I wanted to, yeah, so Jonathan has already got an answer, but let's break this down a little bit. So, first of all, I wanted to ask you a question. What is the dimensionality of x here? So you have P such random variables. X is a collection of P random variables, and each random variable could take value from 1 to D, okay? So in order to completely represent the joint distribution of X, so first let's not talk about Y equals to Y yet. Just think about X. So how many number of parameters you would need, to characterize it? You would essentially need a D by D by D by D, the P such multiplications, like such a tensor to represent the joint probability, right? The tensor would be like P dimensional, but each dimension is length D. Do you agree? Right. So now if that's the scenario, also if you condition on Y, because I'm conditioned on the specific, the random variable Y equals to small y. So it's basically, you need the same number of parameters for characterizing this conditional probability, right? So overall, you need O of D power P to characterize it. Okay, so now the following up question would be, what about the number of parameters to characterize the joint probability? This is a much simpler, I guess, question. Now that you already know that answer about what is now this answer. So how do you characterize the joint probability? I'm given a specific example here that Y equals to -1 and 1. So exactly, you need 2 times D power P. Why? Because when Y equals to -1, you need to completely characterize the X, which is D to the power P. But also Y equals to 1, you also need to completely characterize the X. So you need to sum these two up. So it becomes 2 multiplied with D to the power P. Okay, so now, what I'm saying is, it seems to be very difficult. Sorry. Oh, sorry about that. Here. Okay, it seems to be very difficult to completely represent the joint probability, even if, I have like D, D might, so, it's basically, it's finite, right? I can enumerate the values of X from 1 to D. So it's already a very simplified situation. The only thing is that I have P here. So P meaning the number of random variables in my entire, in my problem, right? So this is so-called the high dimensional if P is really large, because think about, a data set, right? A training data set. So you have these features. So let's say you have 1,000 features. Then in that scenario, each feature can be represented as a random variable. Then you would have P equals to 1,000, right? So each random variable, each feature would be represented as X1, X2, all the way to XP. Although in practice, those features can take much more complex values, not as simple as just, taking values from 1 to D, right? I'm using a very simplified example here to show, even in that scenario, it is exponential in terms of the dimension, right? Which is P here, okay? Dimension meaning the dimension of the feature vector in your training data set. I hope that's clear. This is a little bit confusing. I don't want to confuse people with D and P, right? D just means what are the values I can take for each of my feature. P means what is the number of feature, right? Usually it could be very large because we are dealing with high dimensional data often in modern machine learning. Okay, So now, the naive Bayes, everyone is familiar with it. What is the naive Bayes? Naive Bayes is just simply saying, I wanted to make an assumption on the conditional independence. So basically, the naive Bayes makes the following assumption that the conditional probability of X conditioned on Y equals to some certain Y. It is just a product of the conditional probability of each random variable or each coordinate of X conditioned on Y, right? So this is making an assumption that the X variables here are conditionally independent given Y. Okay. Right. So that's why I'm writing it this way. But actually, I will give you an explanation of why I'm writing it this way later on. So if xi are taking values from 1 to d, then the number of parameters to characterize this conditional probability under naive Bayes would be what? What is the number of parameters? Yes, it's gonna be p times d. Why? Because you only need to characterize these conditional probabilities, right? In order to characterize that. So you have p such conditional probabilities of this form, right? Because you're summing from 1 to p here. So p such ones, and each one would only take you d parameters. So it becomes p multiplied with d, right? So you can see the difference here. Before it was d to power p, now it is dp. So it is a much better, it's a huge save in terms of the representation complexity needed, or the number of parameters needed to represent these conditional probability. Okay, so overall, Bayes network is a compact way of representing joint distribution. And I'm just using a naive Bayes as an example. Of course, Bayes network do not necessarily assume naive Bayes for sure, but based on the architecture of the graphical model associated, it is actually giving you some ideas of what are the assumptions we are making to simplify the representation of such joint distribution and get a more compact representation of this joint distribution. Okay, so I'm using a naive Bayes as an example. I hope that's a very informative example for us to understand the power of Bayes networks. So now, since I've already talked about conditional independence, so let's think about, let's take a closer look at the conditional independence. I'm looking at a graph here, right? This is a, directed, Bayes network, let's say. So a graphical model is a way to represent a joint distribution by making conditional independence assumptions. So I have a graph here. So, everyone knows that in order to have a graph, you need to have nodes and edges. So what are the nodes? The nodes in the scenarios are the random variables. So it's the collection of the random variables. You can give them a name. For instance, I can just name them as integers, right? It doesn't matter, just an identity, just the name of these random variables. It could be I to V, or it could be XI to XV. Yeah, so it's fine. Now the edges, so now what's really interesting is, how do I use edges to represent this joint distribution, right? So the joint distribution have 7 random variables in it. I'm going to use a graphical representation to understand this joint distribution. So the key is how to design or how to find such edges, right? So before that, I first wanted to remind everyone the adjacency matrix. I hope everyone's familiar with that. So the adjacency matrix G of ST equals to 1 if ST are within the edge. So for the undirected one, of course, if you have S connect to T, then GST is 1. Because it's symmetric, also, the GTX is also going to 1. But for directed one, this is not necessarily true. So for the directed graph, I wanted to introduce the notations of parents, child, and root, leaf, ancestors, these descendants, neighbors, right? So parents apparently is just, if you have a parent of S, then it's just the T such that GTS is 1. So there is a edge from T to S. Then the T is gonna be called as the parent of S. Okay, a child is the opposite, right? If you have an edge from S to T, then T is gonna be the child of S. Of course, root is just you don't have parents, and leaf is no children. Ancestors is for any S, right? As long as there is a path from S to T, then the S could be the ancestors of the T. And similarly, if there is a path from S to T, then T is gonna be the descendants of the S. Okay, so neighbors also, if you have GST equals to 1 as well as GTS equals to 1, then it's not as well as, sorry. So as long as one of them is true. So either GST is 1 or GTS 1, it's gonna be a neighbor of the S. Okay, so the in degree is the number of parents and out degree is number of children. So again, this is simple notation here. I hope this is, since this is relatively simple, I'll just go through it very quickly. Now, I promised to talk about conditional independence. So for directed graphical model, such as belief networks, causal networks, and Bayesian networks, so you have this conditional independence. This is very important. So you have an S, which is independent of this set. So, so for S, let's see, you can choose an S. Let's say S is 4, okay? So if S is 4, then, it condition on the parent of S. So what is parent of S? What is the parents of 4? 2 and 3, right? So condition on 2 and 3, S is going to be independent with what? The ancestors of S. So first of all, what are the ancestors of S? 2, 1, 2, 3, and 5, right? Because there is a path from 1, 2, 3, 5 to 4. Now, if you exclude the parents, so it's gonna be 1 and 5. Okay, so conditional on 2 and 3, 1, 5 is going to be conditional independent. 1, 5 is going to be independent with 4. Any questions? I'm using 4 as the S as an example, but you could also use others, right? For example, you can use 6 as S and so on. So this is very important. This is a conditional independence correspondence between the figure, between the graph and the conditional independence in your joint distribution. I'm gonna pause a little bit and see whether there is any question regarding this. We block the path from S to other nodes. So, yes or no, this has to be ancestor. This is not, present. So it is very important to notice that this is the ancestors, not the descendants. Do you see why? Right, so yeah, I hope that's clear. So essentially, if you can find such a conditional independence, then you will have to, like, your graphical model has to be consistent with this, so that this is really hard to say. So in the joint distribution, right, you're trying to characterize a joint distribution, and some of them are going to be conditionally independent. Okay, so this is saying that for as long as you list all the conditional independence in the joint distribution, let's say you list all of them, and then you should find a graphical model representation such that it will be consistent with all the listed conditional independence. I hope that's a better explanation. Right? So how do you make sure that happens, right? So now, based on this graphical model, I'm saying, okay, condition on 2 and 3, 1, 5 should be independent with 4. So you might ask yourself, is this true? Right? If this is true, then this is consistent. This graphical model is consistent with your condition, with your joint distribution. If it's not, then this graphical model is inconsistent with your joint distribution. So it won't be representing the joint distribution. Okay, so overall, what I wanted to say is that, using a graphical representation, you are able to represent these conditional independence very compactly, very nicely, very concisely. Okay, so I don't know if there are other questions, but I'll continue. So we talked about, this conditional independence, but, a lot of you will be curious about what is inference, right? How do we do inference in graphical model? What does inference mean in graphical model? You might have heard about that. So the inference is basically trying to address the following question of, given such a joint distribution, what can we do with it? So when I think about unsupervised learning, I generally think the foundational question is really to estimate the underlying distribution, the joint distribution where your data is coming from. I think that's the foundation of understanding unsupervised learning, or even working, not only understanding but working in unsupervised learning. So this inference, though, is not trying to learn such a distribution. It is saying, if I am given such a distribution, what does that mean? That means that if you've learned such a model, the model is what? It's just a joint distribution, underlying joint distribution, right? So this is like inference. Now you can relate to why I call it inference. So in supervised learning, you have to learn a model, and with the model, you're going to do prediction. Now in unsupervised learning, I have to learn the underlying distribution. And now with the underlying joint distribution, what can I do with it? That's my inference, okay? So now let's say you have such an underlying distribution, which is, using a compact way of representing it using graphical model. So the probability inference is the task of estimating unknown quantities from known quantities. So what do I mean? You observe certain realizations of these random variables. These, let's say the black ones are the ones that you can observe, but the blank ones, the white ones are the ones that are hidden. So what does that mean? You know that the graphical model each node is representing a random variable, okay? So, so then in practice, you can get samples, you can observe realizations of these random variables. And that's what your training data. Your training data are just realizations of these random variables. However, unfortunately, sometimes you don't get to observe all the random variables. You might only observe part of them. In this scenario are the ones that are black. Okay, so you have 3 hidden variables that you don't get to observe. So the probabilistic inference is the task of estimating unknown quantities from known quantities. So you observed these known probabilities, and you also know the underlying joint distribution. Can you infer what are the hidden variables, or what are the hidden values corresponding to these observed realizations of these random variables? Is that clear? I hope I'm not losing everyone. I haven't got a lot of feedback. Any questions regarding this? Okay, thanks, Josh. Okay, great. All right, so now, the question is really, how to estimate unknown quantities from known quantities. So given a set of correlated random variables with joint distribution, right? So now you wanted to use a theta to characterize the joint distribution. It's going to be some function of theta, okay? Of course, the x have these random variables. I'm deliberately writing it in this way. So x1 through xv are the observed ones, and xv plus 1 through from xv plus 1 to xv plus h are the hidden ones. So, so these are the black ones and these are the white ones. So because I said this is inference, so your model is known, that means your joint distribution is known. And therefore the theta that is characterizing your joint distribution is also known. So you know the theta. Theta is your, we can think of in supervised learning is just your model, but now in unsupervised learning is the parameter that's characterizing your underlying joint distribution. Okay, so theta is known. So the probability of xvxh given theta is known with visible variable xv and hidden variable xh. So these are the xh's and these are the xv's. Okay. So inference refers to computing the posterior distribution of the unknown given the knowns. So basically you're trying to characterize computing the posterior distribution here. And how do you do that? Essentially, you are using this joint probability divided by this probability of xv given theta. And this xv given theta is the marginal probability of your observed variables. Well, how do you get that? So you essentially have to summing over, or you have to marginalizing out all the hidden variables. Okay, so this is a very brief introduction about inference in graphical model. Again, like I said earlier, our goal is not really to focusing on graphical model, but to understand the basics of graphical model, which will help us to understand the latent variable models. Okay. So now, I hope this is clear. This is just, what is inference in graphical model. Specifically, this is a directed graphical model as an example. Also, this PXV given theta is the likelihood of a data, also known as probability of evidence. So I think this is very obvious. Everyone knows about it. Okay, so now I've talked about inference, but what is learning? So the learning really refers to, there is an analogy in supervised learning, right? So if you wanted to learn a model, then it's basically learning the theta, right? So now here, it is computing a MAP estimate of the parameters given data. This is the parameters. So the theta hat is just the argmax of this likelihood plus the regularization of the joint or of the prior, which is the logarithm of the probability of the theta. Okay, so first of all, why can I why the data points are conditionally independent given theta, and that's why I can just write it as the summation of the logarithm. So because they are conditionally independent, then the probability becomes the multiplication, and therefore under logarithm it becomes the summation. Okay, so now you can see this, there is a prior here, but if you have a uniform prior, then this basically reduces to maximal likelihood estimation, right? So you're finding the theta that maximize this likelihood. Okay, so this is so-called the learning problem. You can see this is the probabilistic learning. You're trying to maximize likelihood, or you're trying to compute MAP estimate of the parameters given the data. Okay, I hope that's clear. So now let's move on to the undirected graphical model. The Markov random field is also very similar, but a little bit, more complex than the directed graphical model. So again, the conditional independence is very, very important. Actually, I think we can give a better illustration of the conditional independence in the Markov random field. Here, this is the conditional independence property. So what is it? It's saying that if C separates A from B in the graph, then XA is conditional XC, XA is dependent with XB. So if you have this C, so if you take C out, then the graph will be separated into two parts. Then these two parts are independent, conditioned on C. So this is very simple, right? So for Markov random fields, this is a very, very simple, conditional independence property. So now you can imagine that you have to find a graphical model representation that is consistent with the conditional independence that exists in your joint distribution, right? So you have all these conditional independence, you can list them again, and then you can find a graphical model that is consistent with all the conditional independence, right? So as long as there is conditional independence, then based on what is conditioned on, the graph has to be separable if you take the condition out, right? So the condition is the C here, and AB will be separated if you take C out. They will be disconnected if you take C out. So there is no information flowing from A to B because all the information has to go through C, okay? So basically, if you take C out, then they will be independent. So graphically is also very easy to understand. Notice that the C doesn't have to be one node here. It can be multiple nodes. For example, the C can be here, this 2 nodes, or it can be this 6 nodes, and so on, right? And of course, A and B also is a collection of nodes. So we also have this pairwise Markov property, which is saying, this is basically a very, very important property for us to understand whether there should be an edge between 2 nodes. So this property is saying that if there is no edge between the 2 nodes, then the 2 nodes are going to be conditional independent given all the other nodes in the graph. Okay. In other words, if there is an edge between two nodes, then the two nodes won't be in any way conditional independent, no matter what you condition on. Okay. So if you are connected, your two nodes are directly connected, then they are correlated and they can't be conditionally independent given any other nodes in this graph. So I think, is this clear? Is this analogy between the graphical representation and the from a distribution, from the joint distribution point of view, from the probabilistic point of view? I hope this is clear in order to understand the conditional independence in Markov random field. Unfortunately, I don't have time to give you a lot of very intuitive examples, but I think these two properties hopefully would be obvious enough for us to understand this conditional independence. Okay, so now let me review. Actually, I'm going to talk about cliques. So let's review some of the basic concepts in clique. So we don't get lost. So what is a clique? A clique is just a subset of vertices such that every two distinct vertices in the clique are adjacent. Okay, so everything is connected. It's like a complete graph. Now, maximum clique is a subgraph H of a graph. So a subgraph H of a graph is a maximum clique if H is isomorphic to a complete graph and there is no vertex V that is within G but not in H, so that V is adjacent to each vertex of H. So this is actually very easy to understand. So this is saying this is a clique, and this is saying is a maximum clique. Okay, because no other nodes that is within G but not in H, so that that node is adjacent to each vertex in H. Okay. So also there is a simple explanation, which is a subgraph H of a graph G is a maximum clique in G if H is a clique. So, basically there is an edge between every pair of the vertices in H. If H is a clique and there is no vertex in G, but not in H, that sends an edge to every vertex of H. Okay, so this is rather intuitive. Now I'm gonna give you an example. Let's say this is a graph G. So I will first ask you, if this is my H, what is highlighted in my pink color, if that's H, so can you tell me whether this is a clique?
No.
No? Right. Why?
There's no edge between bottom right and top node.
Exactly. Right. So this is not a clique because not every two nodes in the graph is connected. Now, what about this one? Yeah, this is a clique, but okay, spoiler alert, but is it maximum? I already said no. Why is not? Because there is a node here that connects to every, that is in G but not in H, that is connecting to every node in H. So that's not maximal. Okay. Now, what about this one? This is apparently at maximum 1, okay, because this node, first of all, it is a clique because every node is connected. Every pair of nodes are connected. And now this node shouldn't be included because, it is not connected, for example, to these nodes. Okay. So that's a maximum 1. Okay. What about this one? Is it a click? Yeah, it is a click, and indeed it is a maximum click, right? Again, I think, we got the idea. So now this is a quick review of the maximum click. Now with this review, hopefully we'll be better equipped to understand this parameterization of Markov random fields. So the challenge is that no topological ordering associated with an undirected graphical model, we cannot use chain rule to represent P of X. So how should we do that? We essentially propose this idea of potential function, right? So because, we don't have the direction, so we cannot use chain rule, but, the chain rule basically is kind of a quadratic kind of relationship, right? That's why I said undirected graphical model is more complex because we don't have this quadratic relationship. Well, so how should we represent the joint probability? So people have come up with this potential function or some kind of factors with each maximum click in the graph. So now you might want to ask, why do I care about click in the graph? So going back to this, I wanted to go back to this again. So think about this quantity, think about this pairwise Markov property, right? So what is this saying? This is saying that if you do have an edge, so of course, in here it's saying if you don't have an edge, then you have some conditional independence, conditional other nodes. But in other words, this is also saying that if you do have an edge, then there is no conditional independence. Well, if there is no conditional independence, then there should be any factorization. And that's why a potential function is trying to find a minimal thing that can be factorized, and trying to divide the gigantic joint distribution into the maximum clicks in the graph, so that's, you can factorize based on the clicks. But within the clicks, you can factorize across clicks, but within the clicks, you cannot factorize it because everyone is connected with everyone. So you cannot find some kind of conditional independence relationship within the maximum click. So that's the basic idea. Now let's go into the details. So how do we represent the joint probability? So the solution is the potential function or the factors with each maximum click in the graph. So you're going to denote the potential function for a click as the, this is psi, right? I hope I'm not, sometimes I pronounce Greek letters wrong. Hopefully this is right. So psi c of xc conditioned on theta c. Okay, so this is for a click c. Now the psi c can be any non-negative function of its arguments. So it's a function with respect to the theta c, right? So this argument is theta c, but it's trying to characterize some kind of potential for these xc. So xc is a set of random variables within that click. Okay. So the joint distribution is going to be proportional to the product of the click potentials. So the product, basically, you can think about each product as a factor. So what is this really saying? Is saying that I'm factorizing the graph into maximum clicks in the graph. Right. So here is the theorem saying that a positive distribution joint probability of x greater than 0 satisfy the conditional independence properties of an undirected graph G if and only if the joint probability can be represented as a product of factors, one per maximum click. Okay, so in other words, this probability of x conditioned on theta is going to be represented as the product of these potential functions for each maximum clique and divide it by some normalization partition function. We call it a partition function. And the partition function is given by the summation of all the product, summation over X and summation over all the product of the potential functions. So because you wanted to make sure that the probabilities sum up to 1, and that's why you have this partition function in this form. It's just a normalization term. But unfortunately, usually computing the partition function is very difficult. And that's like, computationally very expensive. Okay, so I'm gonna pause a little bit so that we can think more about this equation here. Oh, that's a very good question. So yeah, so would there be any nodes which are not a part of any of the maximum clique?
Well, every node is a part of a clique of size 1, right?
Exactly, right, exactly. So I didn't mention that. So itself is a clique. So in that scenario, yeah, everyone can be in a clique. Well, so now think about this, right? So if no one is in a clique in the graph, no vertex is in a clique, or like, it's only in a clique of size 1. So let's put it that way. So basically means the graph is not very dense, right? Think about it. If there is a clique, the graph is really dense, right? At least within a clique. So if there isn't a lot of clique, that means the graph is not very dense. Well, if there are a lot of cliques, then even the complete graph is gonna be like a clique, right? So then the graphical model is not useful. There is no conditional independence in a complete graph, right? So the whole point of saving computation is because there exists some conditional independence, so we don't have a lot of cliques, right? And some of them, exactly that's what we need. We hope that many of the nodes are actually not part of a maximum clique that is of size greater than 1. Okay. So in that way, we can save a lot of computation in terms of representing the joint distribution, right? So we don't have to be exponential in terms of dimension anymore. Okay, I hope this is clear. And that's a really good question. Yeah, I didn't mention that. People might be confused about it. So thank you for this question. Now, so with this theorem, now we can think about what is this potential functions, right? So representing this potential function, it's very important to know that the potentials are not probabilities. Okay, so they don't have to be between 0 and 1. They should be positive, of course, but they don't have to be, probabilities. Rather, they represent the relative compatibility between the different assignment to the potential. Okay, so you can also think about them as some kind of unnormalized probability, because they are going to be proportional to the probability of that clique, right? The marginal probability of that clique. So for instance, the maximal entropy, the log linear model defines the log potential as a linear function of the parameters. So you can see here, like this log potential is just theta c x c transpose theta c, right? So it's a linear model with respect to the parameters theta c. So the phi c, sorry, this is theta, right? So I hope this is theta, is that right? Okay, theta c x c is a feature vector derived from the values of xc. Right, so you can think about feature vectors as some transformation of the input data or just the input data itself. Okay. So then the log joint probability is just the summation of these linear terms minus your logarithm of z theta. This is the partition function. Okay. So that's becoming the final logarithm joint, a log joint probability. Right, MAP would try to maximize this guy. Oh, that is phi. Okay, thanks. Any questions? Okay, so we kind of stopped. Okay, so we kind of stopped earlier, but next lecture, we're going to use what we've learned about the graphical model, introduction of the graphical model, to learn the latent variable models while tensor methods. And please refer to these slides. So I'm gonna, I think I've already uploaded the slide here. So if you click here, you will find the slides for next lectures and for the one after. Okay. All right. So thanks, everyone. Have a good afternoon.
Thank you.
Thank you.